Welcome to this course on Elements of Mechanical Engineering. My name is Atchuta Ramacharyulu and I am working as an assistant professor in the Department of Mechanical Engineering. Now in this lecture, we are going to see the Introduction to Engineering Materials. Currently, we are in the beginning of third module in the course of Elements of Mechanical Engineering, where we are going to study different engineering materials and their properties and their applications in industries, and also different joining processes like welding, soldering, brazing, etc. Now, if we see broadly, the materials are divided into two types in the perspective of an engineer. They are metals and non-metals. We have different types of materials that are available in the nature. Some are available and some are manufactured according to our need. So, the two major categories of materials is metals and non-metals. So again, there are two types in metals that are related to iron and non-ferrous. So ferrous and non-ferrous metals. So these are the different types of materials available in the nature. Now, if we go deeply, when we study the metals, so in this, we are going to study the metals first. What are the different types of metals available? What are the properties of them, etc. Now, let us see what is a metal. So, the metal is a material which has good strength and rigidity when compared to non-metals. So, the metals, if we take the example of any engineering structure, it contains some kind of metal, because metals can withstand a lot of strength. They can withstand heavy loads. So metals are the materials which can hold their shape and structure even though a large quantity of load is applied, unlike non-metals. The examples for non-metals are glass, leather, etc. And the example for metals are like iron, copper, which are the very famous materials because they have many applications in many industries and in our day-to-day life. So, when we see the basic definition of a metal, they are broadly divided into two types again. They are ferrous metals and non-ferrous metals, because the ferrous contained metals are very large in quantity, even though iron is one of the different metals available in the nature, but iron has many applications when compared to others, and also in different compositions iron can act differently, what we call it as alloys. Iron has many types of alloys. Depending on the composition and percentage of carbon in iron, so it can exhibit multiple properties. And these properties are very different from each other, and they exhibit like different properties and which we are going to see in the coming slides. Now, the iron containing metals, which include all types of iron and steels, are called ferrous metals, while other are specified as non-ferrous materials. So the metals in which iron is the key component, iron and steel, they can be called as ferrous metals. So the examples for ferrous metals are cast iron, wrought iron, steels, etc. And we have some more alloys like silicon steel, high-speed steel, spring steel. So these are the alloys of iron. By changing or adding some proportion of other metals like silicon, etc., we can change the actual property of iron. We know when we are studying the basics of mechanical engineering, like elements of mechanical engineering, we will mostly deal with two types of metals in iron, that is ductile material, that is mild steel, and hardened material, that is brittle material, which is cast iron. We always used to define or compare these two. that is mild steel MS and cast iron CI. So why do we compare these two only? We have many other forms of iron. Even though we compare these two, mild steel, which is a ductile material, and cast iron, which is brittle material. Both of them are opposite to each other and they work differently under different working conditions and loading conditions. Now, non-ferrous metals are the metals which contains no iron. So, we have grouped all the iron metals to ferrous and remaining as non-ferrous. Now, so the non-ferrous are like some of the examples of non-ferrous metals are copper, aluminum, zinc, lead, etc. So when we see closely, all these metals like copper, aluminum, zinc, lead, these are also behave as similar to any iron metal, but they have different properties. See, this copper, this is very peculiar. Why do we use coppers? We use copper where it has a very good property of malleability, like it can be drawn into thin wires. Very thin wires can be prepared with copper, so which can be used in electrical wiring. We cannot make this copper wires with iron. So iron is not so malleable. It cannot be turned out into very thin wires or thin sheets. Where do we use? We use in some kind of filament winding, etc. So copper is a very good malleable metal. It can be converted into very thin wires without damaging its body. Whereas aluminum is different. It has a very good property of it has a very low weight when compared to iron. If we want to compare the strength property of iron and aluminum, if I make or prepare a metal part which can bear some X load, okay, I prepared the body with two metals. One is iron and second one is aluminum. So both of them have the same capacity of load bearing, that is X. Now, when we compare their weight, when we compare the weight of these two bodies, which are made up of iron and aluminum, the weight of the body that is made up of aluminum is very less when compared to iron. That is why most of the aerospace structures or aeronautical structures are made up of aluminum, because the body itself should have less weight because it has to lift or carry everything into the air. Otherwise, it consumes more fuel. Okay. So when compared to iron, aluminum is very less weight for the same strength. Now we have seen that metals are broadly classified into two types: ferrous and non-ferrous metals. And ferrous metals are the metals which contains mostly ferrous as the key component with other add-ons. And non-ferrous metals are the metals which does not have any proportion of ferrous, that is iron. They are completely separate group of metals. Well, they have their own properties. Now, in the picture, we can see there are multiple metals present here. We have brass, aluminum, cast iron, bronze, metal sludge, steel, copper. So these are the different metals which are available in the nature. Some of them are directly extracted from mineral ore and some of them are extracted after refining. So all these metals will have some kind of raw material. That is, iron will have ferrous and aluminum has a bauxite. Like this, different metals have different iron ores. They're called with different names because they have a lot of impurities present in them. So after purification and refining, we'll get the pure form of metals. They are these metals like ferrous and non-ferrous metals. Now, another classification of the materials which are related to engineering are non-metals. So these are completely different. These are not metals at all. They do not have that strength gaining capacity or load bearing capacity when compared to metals. These are simply non-metals, yet they have some more applications, like they can be used for insulation, or they can be used for holding purpose, or they can be used to manufacture belts. We can use leather for preparing belts, which can be used for running the power transmissions, etc. So, if we see the commonly adopted non-metallic materials are leather, rubber, asbestos, and plastics. So, these are some of the non-metals which can be applied in engineering applications. So, leather is a very good example of a non-metal, yet it has some level of load bearing capacity, and it can be used in preparing belts, like they can be used for preparing of the belts which can be used in pulleys or for power transmissions. So nowadays, due to this veganism and not creating harm to animals, the preparation of leather has been declined, even though the leather is being used in many applications in industry. It has somehow reduced, but it is not completely gone. And rubber is another example which can be used for lining. So if I have an IC engine, internal combustion engine, the engine cylinder has to be sealed with some kind of lining that is made up of rubber or asbestos. So what is this property? What is the property required for this lining? So the rubber or asbestos should be in such a manner, they has to seal the body so that no amount of fuel, that is liquid, should not come out of the cylinder. So IC engine has to be properly sealed in order to close the cylinder so that no amount of fuel will come out while working at very high speeds. So that is where we use rubbers and asbestos. And asbestos has some more applications, like it can be used for where we can use cushions, like we can use asbestos for vibration loading capacity, like they can be used as a dampers for vibration. And then plastics. So what are plastics? We know the plastic is the very highly used component in this millennium, and literally every object you see today is made up of plastic. So plastic is a polymer which can be converted into different forms. Even this pen, this is also made up of plastic. Even this computer, even this camera, TV, tube lights, etc. Everything is made up of plastic. So every component that is derived from the polymerization of the plastic has multiple uses. Even though this plastic takes more time to degrade, or it will take more time when compared to other metals or paper. That is why the plastic has to be properly disposed. The only problem with plastic is it cannot be made into very thin parts. It should be as thick as possible so that it can be reused. Because once this plastic material got into Earth's surface, it will block the water that is draining into Earth's surface. It can cause many problems, like plastic has the life of around 400 years. Like for the next 400 years, the plastic will stay in ground without being degraded or decomposition. Okay. So plastic is a very good metal. It is a very good material. But with proper disposal, it can be used in many applications. Now, leather is used for belt drives, as we have already told that, and it can be used for washes. It is very flexible and will withstand considerable wear under suitable conditions. So we know leather is made up of animal skin. After processing, it can be used for different applications. So the modulus of elasticity varies according to the load. When we apply some load on the leather, it acts differently under different loading conditions. Okay, and then we have rubber. So rubber is used for as a packing, belt drive, and electric insulator. It has high bulk modulus and must have lateral freedom if used as packing ring. We have already discussed that rubber can be used as a ring to seal the IC engine cylinder. So that is where we have to use the lateral strength of this rubber has to be very high while when it is used for packaging or packing ring. Okay, so it has to be so strong to withstand lateral loads when it is working or when it is placed inside an IC engine. And asbestos is used for lagging around steam pipes and steam boilers. So asbestos layer, as we used to see, these are mostly seen in boilers, where the boiler parts are lined with asbestos. They act as a very good insulator, and also they insulate the entire boiler for not escaping the steam into atmosphere. So this is a very good insulator, as well as it is a very good it is where it can have a more temperature resistance when compared to other metals. And then when we talk about plastics, so plastics, as we have said earlier, plastic is a very broad material which has wide applications, and also it is very dangerous as compared. So when we talk about the plastics, so plastic is a term applied to a large class of moldable organic compounds which are sold under different trade names. So what are the general names we know for plastic? Like plastics are used in everyday life. They can be used for PVC. They are sold with different names like PVC, polyvinyl chloride, which is a polymer. So also we have polyester, which is used for different applications. Like it can be used to prepare another application, like I will discuss. And then we have polythene. So each and every form of plastic has different applications. So PVC is polyvinyl chloride. It can be used to prepare hard plastic like water pipes or electric pipes. They can be prepared with plastic, that is PVC. And when we study the polyester is used for preparing some kind of sheets of plastic. Okay, thin sheets of plastic. They can be used for different applications. And polythene is the one which we use in our day-to-day life. Like they can be used for preparing plastic bags. So the plastic bags are made up of this polythene. And also we have some other plastics like bakelite, which is very hard. This plastic is very hard. This is used for preparation of like computer bodies or keyboards, etc. So all these parts are made up of bakelite. Now, plastic is it is a moldable material. It can be converted into any type of shape, just like iron. Yet it has more properties than iron. Like it can be molded into different shapes, and yet it has less weight. Okay. When we talk about the load bearing capacity, the plastic will not have that much of load bearing capacity when compared to iron. So in order to prepare a plastic body which can bear equal amount of load as iron, we have to make it so solid, and it does not have that much of ductility. So we'll study what is ductility and how this ductility is the key property of iron when compared to other metals and materials. Now, the plastics are mostly used for in engineering, for bushing, steering wheels, tube for oils and water, automobile tires, etc. So most of these are made up of plastics. Now, when we divide the major classification of plastic, they are divided into two types: thermoplastics and thermosetting plastics. These are the two types of plastics available in the market. This is the broad classification, where thermoplastics are the plastics which can regain to its original shape after reheating. Like, suppose if I have an object, if I melt this off, if I heat this object, this will be converted into liquid form and it will gain some other shape. Okay. Now, after reheating, after reheating is done, when it is cooled down, it will regain to its original shape. Okay. So then this kind of object is called thermoplastic. So thermoplastic are the plastics which can regain to its original shape and size when heating is removed. Whereas thermosetting plastics are the plastics which will not regain its original position and shape and size when the heat is removed. So when we talk about thermosetting or thermoplastic, we mostly deal with heating of plastics. Okay, when it regains to its original position when cooling, it is called thermoplastic. When it does not regain to its original position and shape, then it is called thermosetting plastic. So these are the two classifications of any plastics. Now let us try to study the properties of the comparison between metals and non-metals. We are going to compare some properties between metals and non-metals. Now let us see some examples. So the first property is structure. When we compare the structure of a metal and a non-metal. So in metal, all solid metals have crystalline structures. Okay, they have a perfect crystalline structure. When we take the example of iron, it will have a perfect crystalline structure. When some kind of load is applied on it, it can bear because it has a proper structure at its atomic level. Now, if we take a non-metal, so the non-metal will have mesomorphic form or amorphic form of structure. So they are not that strong when compared to crystalline structures. As we know, crystalline structure is a very uniformly structured form where they can bear more amount of load when compared to non-metals which have amorphic or mesomorphic forms. So that is the first property about structure. Metals are good in this. So when we compare the score of good points between metals and non-metals. So in this, metals has got 1 point. And then when we compare the second property, excitation of easy, difficult valence electrons by EMF, electromotive force. So when we compare the excitation of electrons that are present in the particular material, that is metal or non-metal. So in metals, the excitation is very easy. Simply, if we take the example of copper, so copper has many free electrons, that is why it is a very good conductor of electricity when compared to rubber. So the rubber is a material which does not have any free electrons when compared to copper. So that is why it can be used for insulation. Okay, it does not make current to flow through its body. So the excitation of electrons by using some kind of EMF, electromotive force, is very simple, easy in metals. It is very hard in case of non-metals. That is why this metals has got another point. Now, when we compare the state of these two materials, that is metal and non-metal. So in metals, generally solid at room temperatures. Most of the metals are solid in the form. They can be easily identifiable and they can carry a good amount of load. Whereas gases and solids at ordinary temperature. So most of the non-metals are in the form of gas or in the form of solids at room temperature. Okay. Again, this metals has got another point because generally they are solids. Solids are more stabilized in manner, so they can be used for any kind of applications. Because a gas can easily escape into atmosphere if we not hold it. So that is why solids are more suitable for engineering applications. And then luster. So this metallic elements will have more metallic luster because they are made up of metal. And when we compare non-metals, they do not possess any metallic luster. So what is luster? So it is defined as a property of a metal which will help the metal to be modified or molded. So it can be converted into other shapes. Any metal can be converted into other shape by simply heating and applying some pressure. But non-metals may not have this property. They do not have a metallic luster. Okay, and then so this is another point for this metals. And fifth point is conductivity. So all the metals are good conductors of electricity, because we have seen in the previous point, that is second point, the excitation of electrons is very easy in what we call metals, whereas it is a very tedious task, and it is very hard to excite the electrons that are present in the non-metals. That is why they can be used as insulators. So the non-metals are very bad conductors of electricity. So here another point for metals. So the next property is malleability. So most of the metals are malleable. They have the property of being converted into thin wires or thin sheets, whereas non-metals does not have this property. Okay, even though all metals does not have malleability property, but some properties upon changing the composition of its metals, that are properties of the metal that are present in it. So any metal can be having the property of malleability. So generally iron does not have malleability. So adding some other forms of components like silicon or copper, the malleability of the iron can be increased. Okay, and then seventh one. So ductility. Ductility is the property which enables the metal to be not to instantly break when a load is applied. So it will take some time, or it will undergo some deformation, that is considerable deformation, before breaking. So this is the very good property of iron, that is particularly mild steel, because of this property, mild steel has many applications in engineering. Okay, we will going to discuss in the coming slides what is ductility and its properties in its applications. Whereas non-metals does not have this ductile property. Okay, and then hardness. So generally all the metals are hard. So I forgot to write all the points here. Here another point. So metals are generally hard. Okay, they can carry high loads, and whereas this hardness varies in these non-metals. Okay, so hardness varies from metal to metal. And when we compare the property of electrolysis, so what happens when electrolysis is done? So in these metals, the electrolysis is done from anions. Okay, in non-metals also it is done from anions only. So that is where we can see the property of electrolysis. That is mostly the electrons will be emitted from anions. And when we compare the density is the property which varies from metal to metal or metal to non-metal. And due to this, metals always have high density, because they have a crystalline structure which is closely packed. That is why they are highly tensile. So the density is very high for metals, and compared to non-metals, these have low density when compared to metals. So these are the properties in every situation. Like when we take a particular situation, metals and non-metals, both of them will have their own properties, own good things about their applications. That is why this metals and non-metals have their own applications. We cannot compare them. When there is a point of time where we can replace the metals with non-metals, yet it takes more effort and time. Okay, until then, metals are used for load bearing, non-metals are used for like general applications like insulation, etc. Now When we are studying the engineering materials, we should know these two definitions. These are very popular definitions and they are like basics of mechanical engineering, where without these definitions and without the proper knowledge about these two concepts, the courses, like different courses are there in mechanical engineering, we cannot understand them. Now, the first concept is stress. So what is stress? In engineering materials, stress is defined as when a body is subjected to load, some kind of internal resistive force is developed in the body to withstand the externally applied load. Okay, I'm repeating this definition again. When a metal body is subjected to load externally, similar amount of internal load bearing capacity is exhibited by the body. Now, this is called stress. Now, I have a question like, can we measure stress? No, stress cannot be measured. Stress is an imaginary property, yet it exists, but it cannot be measured until the metal body is broken or it fails. So you can see in this picture, there are two specimens which are being subjected to tensile load. Upon applying some kind of load on this metal body, this is one specimen and this is another one, both of them having different cross sections. Upon applying some kind of load on them, they will be, up to some extent, they will bear the load, and beyond that load, the metals will break. A fracture will happen on the metal. Now what happens? How this stress is acting inside the body. Now, if I apply some kind of load, like if I have a metal rod, if I apply 100 kilograms of load, I'm applying some tensile load. So the load is about 100 kg. So what happens when I increase the load from 0 to 100 kg? So the metal rod will try to bear and try to withstand this load. Okay. So suppose if I take the failure loading capacity of this metal is around 120 kg. Okay. Now I have a metal rod. I am applying some kind of load on it, like up to 100 kilograms I am applying. So the breakage point or the failure load of this body is 120 kilograms. That means if I apply a load of 120 kilograms on this body at this cross section, okay, the body will be failed. That means it will break into two pieces. Observe this. I am applying only tensile load. That means the loading is perpendicular to the cross section. When we see the cross section of this pen, it is a circular cross section. I am applying the load on this point and bottom point. Both of them are acting perpendicular to the cross section of the body. Now when I apply load, I will increase the load gradually from 0 to 100 kilograms. The body will try to withstand the load. Whenever it reaches 100 kilograms, it will try to expand, like it will try to elongate. The length of the body will increase. Whenever there is an increase in the length of the body, the cross-sectional area will reduce. So, whenever this happens, initial cross-section area has been changed to new cross-section area that is less than the previous one. Now, what happens? I am continuously applying the load, 100 kilograms of load. Okay, 100 kilograms of load is very suitable for this initial cross-section. Whenever I am increasing the load beyond 100 kilograms, the cross-section area is decreasing because the body is elongated. It is elongated in this direction. So obviously its cross-section area will decrease. So what happens due to this reduction in the cross-section area and the amount of load that is being applied on the body is increased. So what happens? The body will initially break at some point. Now this entire thing is managed by stress in the body. So stress is the internal resistance of the body which is exhibited when a external load is applied. So beyond the stress, if we apply the load, the body will fail or it will break. Now this is stress. Generally stress is denoted with sigma, and the intensity or degree of distortion is known as strain. So this is another definition that we are going to study next. Now the second definition is strain. Now strain is the difference. It is the ratio by which we can identify how much the body has been elongated when some load is applied on it. Now how do we define strain? So strain is the change in length of the body when a particular load is applied. Suppose I have the same metal rod on which I am applying 100 kilograms of load. When the load is applied on the body in this direction, its length will change. Initially its length is L. Now after applying the load, the length is changed to some extent. It will increase because I am applying a tensile load. The length of the body will increase. Suppose the length may increase by a small amount, that is delta L. So this is delta L, very small change in the length of the body. Now when I apply some compressive load, the length will decrease. That also can be easily taken as delta L because it is change in length. Now this ratio delta L by L. So delta L is the change in length of the body after application of the load, and L is the length of the body initially before applying the load. So we have to take this ratio, and this is called as strain. So strain is the change in length by original length of the body when a particular load is applied on it before failure. We are going to observe this change in length only before the failure. See in this picture, these objects are failed. They are broken. They are broken into two parts. Now whenever there is a breakage or failure happens, we does not take this length into consideration. Before failure, the change in length is taken into this formula, and this is used to calculate the strain. Now so far we have got good knowledge about the two concepts of stress and strain. Now we are going to study some interesting topic, that is stress strain curve of a ductile material. Now why do we need to study the stress strain curve of a ductile material? What is stress strain curve? So stress versus strain is plotted in a graph. Stress on the y and strain on the x-axis. We have to plot a line between these two in order to identify some good properties, and also in order to identify the behavior of metal when it is subjected to loading. Now before going into the explanation of this particular graph, we have to assume some assumptions. The first assumption is the metal which is taken, it should have uniform Young's modulus. Young's modulus value should be uniform, E value. We are going to study what is E and how it impacts the properties of metal. Now E is the Young's modulus. This is the first assumption. It should be uniform throughout the body. And second one is a tensile load is applied on the body. Only tensile load is taken. And third assumption is the metal should have isometric properties. That means in all the three directions like X, Y and Z. In all three directions, the properties of the metal should be same. Okay, then it is called as isometric. Now, With these assumptions, and some more assumptions are there, with these assumptions, we are going to study the stress strain curve that is formed. Okay, now let us see. I have taken a metal rod. When I am applying some kind of load, that is tensile load on it, okay, I am pulling the bar in both directions. So the cross section here is initially taken as like capital A is the cross sectional area. Now, when we want to draw a graph, we can draw by using this stress strain curve while comparing the stress and strain on the body. Okay, so strain is taken on the horizontal axis and stress is taken on the vertical axis. Now, when we compare the different points like stress and strain, this red color line, this is drawn according to the load. Okay, there are two lines here. One is red and another one is in the black color. So we are going to study what is the difference between these two and how they will identify the behavior of the metal. So generally what happens when we apply load from 0 to some x. Okay, now when I am increasing the load, I have to gradually increase the load on the metal plate, metal rod. Then what happens? The stress and strain variation will be inclined like this. That means the stress, whenever the stress increases, strain also increases. Whenever I am applying the load, it is shown as stress inside the body. Due to this stress, there will be an elongation seen in the body. That means the body will try to elongate. Now, whenever there is elongation, we can see some value on the strain. Okay. Now, from 0 to this point, up to this point, okay, so here we are studying ductile metal. Remember this? This graph is only valid for ductile metal, not for other metals. Okay, so the property of the metal which have, like we will study how the ductile property is used by this metal and for drawing this graph. So whenever the load is being increased on the body, what happens? It will slightly increase the variation. So the graph starts from point A to point B. Now what can we understand from this graph? Whenever there is an increase in the load, the variation will be uniform. That means it is linear. This can be called linear. The stress and strain are linear in this manner. Now, when the load is further increased, that means more load is being applied on the body, then what happens? At some point, we will have yield strength. This point B is called as yield strength. That means at this point, the body will bear the maximum load. Okay, only up to yield strength we can give loads. Okay, and after yield strength, what happens? The curve will slightly decreases and again it will rises up. Okay, after yield strength point, the graph will slightly decrease. That means the stress and strain are slightly varied. They are no longer linearly related. Now they are cubically related. Okay, they are in the form of a curve. Now, at this point, we can understand that stress is somewhat reduced, but strain, it is still increasing. Okay, and again, after the yield point, the graph will go up again, this line. Again, the stress value will increase in the body along with strain. So, from here to here, this point is called ultimate strength, where we can actually apply a load on a body up to this point, ultimate strength. So beyond this ultimate strength point, a body cannot be loaded because it will lead to failure. So ultimate strength is the point where the body has the highest load bearing value. Beyond this highest load, we cannot apply. That is why it is called as ultimate strength of the body, because beyond this ultimate strength, the body will tend to fail you. Okay, it will simply fail or it will break. Now what happens? At this point, we can see the formation of necking. That means whenever a load is applied on this body, on this metallic rod, we can see the formation of a decrease in the cross-sectional area. So initially, the body is like this. So this is 1 and this is 2. Initially, the body is in the form of 1. Now when I'm trying to apply more and more load on the body, what happens? It's some cross section at any point on the surface will try to reduce. Because I am elongating in this direction, the cross section area will decrease at some point. Now due to this decrease in the cross section area, so what happens? Because of this decrease in the cross section, I am applying more and more load, and due to this, the weight, the strength of the body will decrease. The amount of stress it can generate will decrease, and ultimately it will go down. So after ultimate strength, the graph will go down because the cross section area is decreased. Okay, so and ultimately at this point failure takes place. So whenever the strain has reached from 0 to this point, this is some C. Whenever it reaches C point, the failure will take place. Okay, so this is engineering curve, that means engineering stress and strain relationship, whereas this is generally given in theoretical form, but in actual form, that is true stress is calculated. The stress will be calculated differently. The stress strain relation graph also changes. Now, we have studied this red colored curve, that is starting from A and going up to yield strength, and after that yield ultimate strength, and after finally failure. Okay, so this is the curve that is generated theoretically. But what happens? Because we have taken an assumption, that is the cross section area is same throughout the process. Cross sectional is same throughout the process, which is not true, because when we apply load, the cross section is decreasing. So that is why we have to modify this graph due to the decrease in the cross section upon applying some kind of load. So then this entire thing will change. This entire theoretical graph is no longer valid because the cross sectional area is being decreased. In practical applications, we have to consider this black color curve because it is more practical than the theoretical red color graph. So what happens when the load is increased from point A to point B? It is similar to that of the linear, the relation is linear as we see in the engineering curve. Okay, the red color line is called engineering curve. It is written here. And the black color line is the true stress strain relationship. Like after increasing the load, the cross sectional area will try to decrease. Now at this lower cross sectional area, the body is still able to bear the load. Okay, when we see the formation of necking, okay, at this point the necking will be seen. So from this area, the necking means decrease in the cross sectional area will be seen. Even though the body is being, it is reducing its cross sectional area, it is still able to bear some more load on itself. That is why the stress graph should go higher, not downwards. Because there is a decrease in the cross section area due to this new cross sectional area which is less than the original cross section. Even though the cross sectional area is less, it still can bear more load or it can exhibit more stress. Okay, that is why this graph should go up. The stress bearing capacity is more even though the cross section area is less when compared to initial values. So this graph will go up, and finally at some point due to elongation, the object or the metal rod will fail or it will break. So this is true stress-strain relationship, where we are going to consider the varying cross-section. In the engineering stress-strain relation, we don't consider the varying cross-section. We assume that the cross-sectional area is same from initial to the final point, that is no load to the failure point. Okay, so this is all about the stress-strain curve of a ductile material. Particularly, we are going to study this. This graph is valid only for ductile metal. When we want to study the graph or the relation for a brittle material, it is completely different. So from this graph, we can understand that a ductile metal will have more load bearing capacity. Load bearing capacity is more for ductile metal. More load bearing. That means whenever a high amount of load is applied on the metal, it will not break instantly. It will try to elongate itself. It will try to bear more amount of load and it will show some deformation. And after that, finally, when the load is very high, beyond which the metal rod cannot accept or it cannot bear that load, it will break finally. But it will not break instantly. It will show some deformation. So, what is the use of this ductile metal? Because it shows some kind of deformation before failure, it can be used in most of the engineering applications where we are dynamically applying loads, so that these bodies are, most of the automobiles and aerospace bodies are made up of this ductile metals only, because we can identify for deformations, we can identify the deformations so that we can understand the body is being overloaded and we can change the body or we can change the design. Now we have another kind of metal. They are brittle metals. So what is the difference between ductile and brittle is, so ductile metals will show some form of deformation before failure. They will show deformation. When load is applied on the ductile metal, they will show remarkable deformation before going to failure. Now, in brittle material, they don't show any deformation. They will simply break. They will simply fail when load is applied. So that is what we can observe from this stress strain curve, where the load is increased from 0 to some extent, and after that there is a small variation, that is a small curve is observed, and beyond that point the metal will immediately breaks. So this is a property of a metal which does not show any kind of deformation before failure. Okay, so in this graph we can see, we only use the theoretical graph in most of the applications. When we study engineering materials, we will study the engineering graph only, engineering stress strain relation, that is red colored graph. So we will design most of the engineering bodies within this limit only, before the yield strength only. Okay, even though they are prepared for more loads, the limit will be taken within the yield strength. Okay, so we have to consider the factor of safety, where when a more amount of load is applied on the metal body or a metal element, so it can go up to ultimate strength, but it will not go to failure. Okay, we will design any metal object related to engineering within this limit only. Okay, so suppose we take the example of a motorcycle. So the motorcycle is generally designed for 2 persons, each of 100 kilograms weight, 100, 200. So this is the maximum load bearing capacity of any motorcycle, but we will use the motorcycle for riding more than 2 persons, like 3, 4. In India, we can see this. More than 2 persons will always be sitting on motorcycles. Yet, the springs or the wheels, not any part of the motorcycle will not fail, because they are designed within the limit, within the yield strength limit. That is why they are safe, because even though the load is more than the yield strength, it can bear up to ultimate strength point. And after ultimate strength, it will definitely be broken. That means if four persons of like 100 kilograms, 400 kilograms weight is applied on the motorcycle, and the motorcycle is going at a very high speed, and if it may go into some kind of pothole on the road, it will simply break. The springs will simply break. Okay, we will always keep in mind the factor of safety, which is always close to 2. That means if a body has to bear 100 kilograms of weight, it is designed for 200 kilograms. That means more the factor of safety, more the strength of the body. That means it can bear more load, okay, when compared to the designed value. So when we study the stress strain curve of a brittle material, it does not show any kind of deformation. It will simply break. That is what we can infer from this graph. And that is all for today. We'll meet in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.